This is a plenary lecture for the Bailey Award. The Marilyn and Sturges Bailey Distinguished Member Award is the highest honor of the Clay Minerals Society and is awarded for scientific eminence as presented primarily by scientific publication, outstanding original research in clay science, and by the impact of this research on clay sciences. Technical contribution to clay science is the sole criteria for this award. Denny Eberl is receiving this award for his dedication of contributions to clay science and the Clay Minerals Society. With over 150 publications, thousands of citations, and numerous patents, Denny's career contributions are many, but he is most recognized for his contributions to our understanding of how crystals grow. So this paper is an example of the work of Denny that is so fundamental to our society. Deducing crystal growth mechanisms for minerals from the shapes of crystal size distributions, published in 1998 in the American Journal of Science. It's fundamental to our understanding of crystal growth in open and closed geologic systems under surface and supply-controlled growth conditions. This is a photo of Denny and Bob Reynolds at Dartmouth College in New Hampshire in 1965. Denny got his bachelor's degree at Dartmouth College, and like all alums of Dartmouth Earth Sciences, took clay mineralogy from Bob Reynolds, who is a pioneer in clay science. He studied Central American volcanoes with Sturges as well, and these beginnings focused his interests on volcanic emissions to form bentonites and their value as records of geochemical conditions at first nucleation and over time as crystals grew in response to burial and changing pore fluids. Denny has a profound literary interest after Dartmouth. He studied writing at the University of Syracuse and then received his PhD at Case Western working with John Howard. He first taught at the University of Northern Illinois and was tenured at University of Illinois Champaign before he became division chief at the U.S. Geological Survey in Boulder, Colorado in 1981, where he is now emeritus. At the USGS, Denny's group worked to invent new techniques for studying minerals using X-ray diffraction, X-ray fluorescence, polymer absorption, crystal growth simulation, and wrote computer programs to do the calculations. The most famous is his X-ray interpretive software called RockDoc. And if any of you have used RockDoc, the manual begins with a poem by Wallace Stevens called The Motive for Metaphor. I had no idea what this poem meant, so I asked Denny, why did he choose it? And he said, it just was something to ponder while waiting for RockDoc to run, which in the old days took about 45 minutes to find out that your pattern didn't match the minerals you thought were there. It was a commitment and an adventure to find the final result, the final dominant X. I still don't know the nuances of this poem, but for me in the context of RockDoc, I think that it means finding X, the answer, or interpretation of the X-ray pattern, ends the anticipation of the quest. Finally, one cannot introduce Denny Eberl without revealing his eminent stature as the clay doctor, always notated not a real doctor, in the original CMS newsletter. The Clay Doctor was a satirical column written about clays and clay mineralogists, originally in the form of a Dear Abby column advice column. I share with you this one example. Dear Clay Doctor, why is it through the years that the French have had such a strong research interest in clay minerals? Cherchez, Le Fouillet, Brussels. Dear Cherchez, the French nation has some of the world's finest wines, restaurants, and perhaps the finest lifestyle altogether. Therefore, it's natural that they should want to study the world's finest minerals. In addition, French scientists have long realized that research on Euroclay will lead to key understanding. The joke is that it's a bilingual pun. Euroclay in French means the key. Therefore, naturally, research on Euroclay leads to key understandings. So, the series of Clay Doctor articles was written by somebody with wit and a poetic mind beyond clay science. So it's my great pleasure to introduce to you today the Clay Doctor and Bailey Distinguished Award recipient, Dr. Denny Eberl.
Thanks, Lynda. My boss at the USGS asked me once, why do you study such a tiny thing? Tiny and insignificant. And I said, clay crystals are very tiny, but there's a lot of them. And did a calculation once that RM30 illite that has a fundamental particle thickness of 12 nanometers, that there are 200 trillion particles in 1 gram. So it's really some of the finest material in nature. This is what got me into clay mineralogy. My roommate Ed Perry and my thesis advisor John Howard did this study of Gulf Coast clays, going down a borehole, and found that illite layers increase, or the expandable layers decrease with increasing depth and temperature. And the question is, why does this happen, and how does this happen? And this study was made possible by the computer programs of Bob Reynolds' NUMOD program, where he could actually model these clays and model the X-ray pattern and try to understand what's going on. And so this is a cartoon of a randomly interstratified illite smectite going with illite layers and smectite, expandable smectite layers with exchangeable cations. This one is 1, 2, 3, 4, 5, 6 layers, 2 of which are fixed around potassium. These are illite particles. And so this clay is 67% expandable, or 33% illite. And it goes from a randomly interstratified clay to an ordered clay. In other words, illite, smectite, illite, smectite, illite, smectite, illite, smectite. And this is actually, it turns out, a rather crude way of looking at this, and I'll show you why later. So these particles, which Michael Wilson and Paul Nadeau and others have called fundamental illite particles, are actually illite crystals. They are crystals. And you can see that in the next slide. Here's an illite crystal with spiral growth on the surface. And here's a illite crystal with a nice termination on the end. Just the finest crystals in the world. And here's a very famous picture taken by McCarty, Wilson, and Tate of North Sea illites. And this shows what's going on here. We see the fundamental illite particles, which are crystals, and they fall on top of each other on the slide. And you can see how thin they are by this particle here, showing through the other particle. They're like wet noodles. And what happens is that these particles fall on top of each other and swell at their interfaces. They have water on their surfaces, and this forms mixed layer clay, mixed layer illite smectite. These tracks here are shadows. If you know the shadow, platinum shadows, if you know the shadow angle and can measure the thickness of these bright spots, you can measure the thickness of the particles. And of course, it takes many hours to do a single sample, and you can only make about 100 measurements. But there is a way of measuring 1 billion samples in a few minutes, and there's an X-ray method called the Berthold-Warren-Auerbach method. which really opens up the possibility of studying these particles. So a lot of people have trouble with this, looking at this two ways at once. One is the McEwen crystallite viewpoint, and the other is the fundamental particle viewpoint. So from the McEwen crystallite viewpoint, which is what everybody has used in the past, this is the crystal here. And this is what shows up on the X-ray machine. And from the fundamental particle viewpoint, we look at the individual particles rather than the whole crystal. And so from this is a mixed layer illite smectite here as a McEwen from the McEwen crystallite viewpoint, and these are the fundamental illite particles. This one being the fundamental smectite particle, and the other one is illite particles that are. This is each 2-to-1 layer is worth about 1 nanometer. So this is a 2 nanometer thick particle. This is a 4 nanometer thick particle. And so both ways of looking at these. At this situation is they're both valid, but it's my contention that it's better to look at the fundamental particles than the McEwen crystallite, because what we're interested in is the crystal growth, and these are the crystals, rather than how they stack on top of each other, which is the McEwen crystallite. So here's some distributions of these fundamental particles, these illite crystals. And there's two main shapes to these distributions. This is by the Berthold-Warren-Averbach method, where you look at an X-ray pattern and analyze it and get the shapes of the crystal size distributions. And there's two main shapes, which is log normal and asymptotic. And this one is from the Silverton caldera. This is from a hydrothermal vein. And this is from the wall rock right next to it. And this is probably formed at a higher level of supersaturation than this one. The Berthold-Warren-Averbach method was invented back in the 50s, simultaneously by Berthold in France and Warren-Averbach in the States. And it was used to look at metals, at strain in metals. And with it, we can look at strain also, but the main use in clay mineralogy is for looking at mean thickness, crystal thickness, and mean and the shape of the crystal size distribution. So, this isn't going to show up. Well, there it is. Oh. There it is. So this is a NUMA calculated X-ray pattern here, and it was analyzed by the Berthold-Warren-Averbach method. When I calculated this, I put in a very special particle size distribution to see if I could recover it. And this is the particle size distribution recovered. It spells the word mum, thickness versus frequency. So all of this information is contained in this X-ray peak, which is analyzed by Fourier method. And what you do is you plot the Fourier coefficients against n, which is the same as thickness for an illite layer. And you take the steepest slope of this curve and extrapolate it to a Fourier coefficient of 0, and this gives you the mean thickness of the fundamental particles. And if you take the second derivative of this slope, this gives you the particle size distribution. This is done all automatically in the program Mudmaster. So you just feed in your X-ray pattern and come out with the answer. And this is very accurate for natural clays also. Here is we've studied it, compared Mudmaster measurements with using TEM, fixed K, surface area, and AFM, and the best study was done by Dudek et al., where they used HRTEM to study see if their method gave accurate distributions, and they're extremely accurate distributions. So, but in order to study an illite, you have to prepare the sample, because you have to get rid of the swelling, because swelling also broadens X-ray peaks. So there's two methods to get rid of the swelling in your clay. One is to collapse the clay by heating and potassium saturation. In this case, you measure the thickness of the collapsed McEwen crystallites. The other way is to osmotically swell the clay by putting in sodium or lithium. Lithium is best. And then treat it with the polymer polyvinyl pyrrolidone, PVP, and then heat it. And when the clay tries to come back together, it's kept apart by the PVP polymer, and then you can measure the thickness of these particles. So this is an example of this method. I hope the rest of the slides can come through. Well, this is a K-heated one, plenty of light. This is a PVP treated one. Unfortunately, the one master is not going to come through there. Oh, there it is. So here we see that for the collapsed McEwen crystallite around potassium, get a mean of about 10 nanometers and a log, almost log normal distribution. The red curve is a theoretical log normal. This is the actual data. And then for the lithium-treated PVP sample, we get a mean of, I don't know what that is, 5 nanometers and a perfect log normal distribution. So here is the McEwen crystallite again with the fundamental particles, made up of fundamental particles. And the nomenclature is this is a 124 McEwen crystallite because this is 1 nanometer. 2 nanometers here, an elementary illite particle, and 4 nanometer thick crystal here. So, in the past, we've used a Reynolds-Newmont program to model these things. A parallel program was developed in the former Soviet Union by Sakharov and Girtz. And in the Newmont method, you dial in the pattern. So you put in you guess the number of illite layers, and you guess the type of ordering you have, you guess the thickness crystallite distribution, and you manipulate these parameters until your pattern matches the real pattern. Now, with the Statman method, and so you make use of the interference function here for the crystal thickness distribution. The Statman method, most of the inputs are experimental thickness frequencies from MudMaster. So the pattern shape is predetermined. And so this is the Statman program. It's called Statman because it manages stacks of illite crystals. So it starts with the illite crystal fundamental particle thickness distribution from the BWA method. It assumes the illite crystals fall randomly on top of one another and swell at the crystal interfaces. Then calculates the proportion of each type of McEwen crystallite, having up to 4 illite crystals per stack, and up to illite crystals that are 10 nanometers thick. Then calculates the X-ray pattern for each type of McEwen crystallite and adds them in the proportion of their frequencies to form the final pattern of mixed layer illite cement type. And so here's some of the output from MudMaster. You saw graphs of this before, and this is the actual data. And let's say you want to calculate, let's say you have McEwen crystallites that are four layers thick. And say they're 2, 3, 4 crystal. So you would multiply 0.58 times 0.58 times 0.17 times 0.1, and that would give you the probability of the occurrence of that type of McEwen crystallite. Now, if with crystallites that are 1 to 10 nanometers thick and 4 on top of each other, this gives you 10,000 possibilities of probabilities that you have to calculate. And then you calculate the X-ray pattern for each type of McEwen crystallite, and add that together according to their probabilities, and you end up with very realistic looking X-ray patterns. This is for individual McEwen crystallites. Here's one that's a 2-2 McEwen crystallite, so it's 2 particles thick, each particle being 2 nanometers thick, and that's what that X-ray pattern looks like for that particular McEwen crystallite. Here's a 3 particle 1, 3, 2, 3. You see very complex patterns for these individual McEwen crystallites, but when you add them all together, you end up with very realistic looking X-ray patterns. So this is the final proof of the fundamental particle concept. Here's the measured pattern for this clay from Montana, studied by Altana and then later by McCarty. The measured pattern, the calculated pattern. These are a little bit low in intensity because the sample was very thin when it was measured. And it looks pretty good. It's not as good as a Newmont pattern, which is dialed in, but close enough, I think. Here's the glycol one. This one was air-dried, using the same frequencies for the fundamental particles. This is the glycol one, measured and calculated. There is one problem here. You can see this little peak, which shouldn't be there. So I don't know, I didn't have time to trace that down before I retired. So maybe if I'd had a stack of 5 particles, it would just disappear. I don't know what else. Here's K heated one. And notice it's hard to see from this. Oh, here's PVP1. Notice that the calculated pattern even reproduces the noise, which Newmont doesn't do. And this noise, if you've ever tried to take it out by running your pattern more slowly, you realize you can't take it out. That's because it's a part of the pattern. It's all these little peaks from the McEwen crystallite shown. Here's a K heated one. Looks pretty good. So these are the 2 main types of illite particle distributions, the log normal and the asymptotic. And the fact is that all other minerals you look at, these are the common distributions found for them, whether they're clay minerals or other kinds of minerals, diamonds from meteorites or calcite crystals formed in lakes. They have either the log normal or the asymptotic types of distribution. So what's going on here? By studying illite crystals, we found a general law for all crystals. And for example, here's some other log normal type distributions for microcline from bugs near in the Pike Peak batholith and calcite. We always compare the log normal distribution in red here to the real data with using the chi-square test. And here's a zircon. I'm not sure where that's from. Log normal also. This is sphene. This titanite is not log normal. So something else is going on here. Everything that's used to the right is not log normal. It's a very specific set of distributions of shapes, log normal shape. So, and notice that this log normal distribution is measured in centimeters, measured by a ruler. This was measured in with a microscope in millimeters. And the clay ones were in nanometers, and they're all log normal. And here's some asymptotic distributions from some other kinds of minerals. Flotobite, this one was measured by Baronet, synthesized by Baronet, who first turned me on to the idea of looking at crystal size distributions. And silver bromide from experiments at Eastman Kodak, magnetite measured by Cashman and others, from the metamorphic rock, calcite, I forget where that's from. And so how do we keep this log normal shape during growth? Here's illite measured in nanometers, microcline measured in centimeters, both log normal. In fact, if we made a reduced plot here, divided the diameter by the mean diameter and frequency by the maximum frequency and superimpose them, they go on top of each other. They'd almost coincide. which means that the variance is the same for both of them, very similar. So the way to do it is with the type of growth that we have. So let's say we have two crystals. This crystal number 1 is 1 micron, and it doubles in size going to 2 microns. So what happens to crystal 2? You can't see this effect unless you have more than one crystal in the system. So crystal 2, there's two ways it could happen. It could have constant growth. In other words, this one added 1 micron, so this crystal could add 1 micron. Or we could have proportionate growth. This crystal doubled, and so this crystal doubled, and the crystal size distributions will look very different. So in constant growth, crystals 2 is always 1 micron larger than crystal 1. And in proportionate growth, crystal 2 is always twice as large as crystal 1. And of course, proportional growth is really a scaling law, and this is the only way to preserve log-normal distributions as crystals grow. The shape stays the same. It's like a model car where you, if you added to bring it up to the size of a real car, you would end up with a slightly deformed cube. What you need to do is multiply to make the car look like a car when it gets to be the car size. So this isn't rocket science. Constant growth, the equation is the former size of the crystal, diameter of the crystal. You add a constant to it to get the new size. And with proportionate growth, you multiply by a constant to get the new size of the crystal. So if you have 1,000 crystals, you would multiply each by the same constant to get the new crystal size distribution. Actually, I prefer to write this formula here, like in this form, where k equals k plus 1, and we'll get this form for the formula, and we'll see why in a minute. So we actually tried this experiment, but we made this box with a transparent top so we could measure the crystals and flow a potassium solution through here. We started working with other clays, with other crystals other than clays, because it's just easier to work with them, and the same crystal growth laws apply. And you can see that with time, this is how this crystal grew. And the bigger crystal, I don't know what is it, the bigger crystal grew faster than the little crystal. And this is proportionate growth. It's called size-dependent growth, and for a long time in crystal literature, it was considered to be an oddity to have size-dependent growth, but this is actually the way that crystals grow most of the time. So just to make this point again, here's these are calculated by the program Geological, which growth according to the law of proportionate effect and by writing. So we start out with a log-normal distribution with the beta square. The beta square is the variance of 0.37. If we do proportionate growth, we end up and double the size, mean size of 20. We end up with the same variance and log-normal distribution. However, if we do it by constant growth, and this is the growth law that most people use in geology, it completely distorts the distribution. So here's an experiment we did with calcite. We started, let it grow for 5 hours, and we had a median of 7.8 microns. You have to measure these things using a microscope. We found that laser measurements were not accurate. And so, let's see, it's going to show up. So if we would try to model this second curve, which is almost doubling in size, and if we try to model it with a constant growth, we end up with this red curve, and proportionate growth, we end up with the correct curve for the distribution. So how do we get the log-normal shape to begin with for all these minerals? And there's one way to calculate a log normal distribution, and that is by the law of proportional effect, which was discovered around 1900. And this is the diameter of the crystal plus a random number times the diameter gives you the new diameter crystal. So and then the new diameter is fed back into the equation again and again and again. This equation is iterated. And so here's a sample calculation for one crystal. First cycle, start with size of 10 microns, say. Random number comes up 0.5 times 10. You get a size of 15, and you take 15, feed it back into the equation, and get a new size of 16.5, and a new random number comes up. And this is for a single crystal, but the Geological program does this for 1,000 crystals. And by the time you've gone through 2 or 3 cycles with 1,000 crystals, you have the log normal distribution. And as we go through these cycles, the variance increases during surface limited growth. It's called surface limited growth because the slow step is the incorporation of the material into the surface of the crystal. And so then how do we get the shape preserved? Eventually it reaches a point where it can't, the transport of the material to the crystal surface can't keep up with the requirements of the surface. And so we add another thing to the equation which limits the amount of material transported to the surface during each cycle. And what happens then is that this becomes small with respect to the size of the crystal, and this becomes effectively a constant. We still can't predict how fast the crystal is going to grow, but we can predict the distribution, which is multiplying by a constant for the distribution. In this case, the variance, instead of increasing, remains constant in the transport of growth. So here's the equation for the generating the log normal shape. And it gives us an insight into crystal growth. For example, we can't predict how fast the crystal is going to grow because it's multiplied by a random number here. So we can't predict the individual, but this is an equation that's both random and ordered at the same time because the random number follows a rule. And so whereas we can't predict the individual, we can't predict the distribution. I think a lot of things in nature work this way. Reynolds once told me when I was a young student, if 2 scientists do an experiment exactly the same way, you'll come up with exactly the same answer. I'm not sure he was right now. I think that there may be a randomness built into the nature. So this is surface limited growth and transport limited growth. This one, the variance increases, and this one, the variance stays the same. And so the log normal distribution created at very small sizes then is preserved by transport limited growth as the crystal get bigger. Now, how do we get the asymptotic one? And the asymptotic distribution is formed by crystals nucleating as previously formed crystals are growing. This leads to this sort of shape. This is actually an experiment we did, and it produced this type of distribution. And what we did was just keep continuously adding new calcium to the solution, continuously nucleating, and crystals end up with this type of distribution. Now, why do we get proportionate growth? And we try to experiment with potassium alum crystals. Here's an example of some of the crystals. If you want to look at these later, I have them in my pocket. And we suspended them in a solution of potassium alum, which was allowed to evaporate. And we started with crystals of different sizes, and and you can see that if if the solution was not stirred, we ended up with constant growth. Although the crystal added about the same amount of material. If we stirred it, then we ended up with size-dependent growth, proportionate growth. So it's a matter of how the material is transported to the surface. And in nature, it must be that most crystals get their material not by diffusion, but by affiliation. So we try to bring on constant growth by growing calcite crystals in a silicon gel. This doesn't show up very well. But we found that right here, in this part of the system, we had some, and we used silicon gel because we wanted to promote diffusion rather than advection. And we found that in this part of the gel that there was evidence for constant growth, but it didn't come in until the crystals were about over 100 microns in size. So it's very small sizes, there's always proportion growth. But at larger sizes, you can make constant growth if you limit the advection. So this is to show you what alpha and beta squared mean. Alpha is the natural log of the natural log mean. Beta squared is the natural log variance. There's two distributions. One has the same mean. They just have the same mean, but different variance. And these have the same variance, but different means. For a log normal distribution, that's all you need to know is alpha and beta squared to calculate the distribution. But this alpha and beta squared are also helpful in looking at other types of distributions. So here's some experiments we did. This calcite with a very small variance, very small beta squared, produced by oscillator Raven. I'll talk about that in a minute. And then this is the log normal distribution with a much larger variance. So for getting back to illite now, this is an alpha beta squared diagram where the variance is plotted against the mean. And this is the Geological calculation. If we start out with illite crystals 2 nanometers thick, right here, and we nucleate them all at once, 1,000 crystals, and then just let them grow. 1 step, 2 steps, 3 steps, according to the law of proportional effect. They will follow this line through alpha beta squared space. And if we nucleate and grow, so in other words, we nucleate 100 crystals, and then we nucleate another 100 crystals and let the first 100 crystals grow by the law of proportional effect. Nucleate another 100 crystals and let the first 2 grow another step according to the law of proportional effect. Then we follow this curve. And this is where we get the asymptotic distribution, and this is where we get the log normal distribution. And here's some actual data plotted here. And you can see that they follow this curve pretty well. These are log normal distributions, and then alpha beta squared follow this curve. And asymptotic distributions follow this curve. Then we came across some complications. Some of them plot out in the middle of this diagram. And so let's see how we get this sample here, 1901, how we get to that place. And what we do is nucleate and grow, nucleate and grow, nucleate and grow, and then we stop nucleating and just grow, and then it goes out in this direction. And after 3 of these, we end up with a distribution that exactly the Gallop simulation exactly fits the measured distribution. So we can look at these illites and tell what the reaction path was. But sedimentary illites, which may come from several sources, won't fit in this field. These are illites from the Yukon River, and they have several sources, and they fall outside the field for illite crystals. So just to summarize, there's the log normal distribution, distribution shape, which is very rare in nature. And this is the asphalt shape, the reverse skew of the universal steady state asphalt distribution. And this was calculated theoretically by Lifshitz, Swiarzov, and Wagner. And if you start asphalt ripening is where the fine crystals, which have a higher surface area, dissolve to give material to the bigger crystals which are growing. You will always end up with this shape of distribution if you start with fine crystals. So we were able to reproduce this many times in the laboratory. And the trick is to get a very high level of supersaturation where your nucleate particles are extremely small. And then they'll develop this shape of distribution. And this has been seen in nature for some garnets. Now, Carlson wrote a paper saying this can't be asphalt ripening because the particles are too big. They didn't have, there wasn't the difference in surface area to form asphalt ripening. These in the decimeter range. I told him it wasn't formed in the decimeter range, it was formed extremely small, and the nanometer range preserved, and that shape was preserved by proportionate growth, like he did in this. Science advances one kilo at a time. So here's the asphalt shape. This is produced at omega of 100. That's 100 times saturation. And then the log normal shape is produced at omega of 40. So it's due to extremely fine crystals being unstable and dissolving and giving material to the larger crystals. And then the shape is preserved by proportional growth. So here's a plot of the distributions formed at different levels of supersaturation. So at omega of 40 from the log normal distribution, omega of 100, this is the log normal distribution, omega of 100 we form the asphalt distribution. And then an intermediate 69 we form something that's intermediate between the two. Now, where do we apply this? It turns out we can apply it on Mars. These are what are called Martian blueberries, which are concretions, very small concretions that were found by the Opportunity rover. There are millions of them all over the floor of this crater. And Royer wrote me about it. Measured the size distribution from the photos, going from Eagle Crater to Victoria Rim. And it turns out that in Eagle Crater, we have the asphalt distribution of these concretions. And the Victoria Rim, we have the log normal. And in between them are intermediate ones. So we're looking at a concentration gradient here, probably on Mars, going from crater, which is a sunk, presumably, maybe has higher levels of supersaturation when these things form, to Victoria Rim. So here's the main types of distributions. Log normal, asymptotic, asphalt ripened, very rare, never seen in clays. And you can get other kinds of distributions too. For example, with this one, we nucleated some calcite and let it grow for a while, and then we nucleated it again. You couldn't even see the crystals, and then when they grew up to the size where we could see them, we measured them and we found the binaural distribution. So it's recorded in history of the first formation of these crystals. Now, to apply this to illness, here's a distribution in blue found for illites from Glarus Alps. I was working on this with my project and he fell out and he didn't work on it anymore. But you can see that this distribution is not well known. Doesn't follow the curve. But if we decompose this into two log-normal distributions. And it fits pretty well in the summation curve. And since we know the shapes of these things, we can know how much of each one of these there is. If we have two samples with different amounts of these we have two samples, then we can measure the argon and potassium in each sample. We can solve the two simultaneous equations for the date of each one of these, and not have to make any separations at all. But this looks a little bit more complicated. It looks like there's maybe some other things going on here, some other events. But let's see, so there would be 2, 3, 4, 5, maybe 6 events. And so if we have at least 6 samples, we measure the potassium argon from each sample and know how much of each one of these there is. We can solve the simultaneous equations and completely know the history of the sample. So there's lots of people to thank on this. A lot of these people spent some time in my lab, and I thank Roosevelt and Lynda for the many months that I spent in their labs. And most of the early crystal growth work was done with Jan Schultz and Dick Glarus. And the later crystal growth work was done with an excellent experimentalist, Dan Kyle at the USGS. So thank you very much. I don't know if there's any type of questions or not. Yes.
So, very interesting talk. I'm not in this field, but maybe just ask a naive question.
Yeah.
So, is the crystal growth related with the suppressed saturation state of the minerals in the solution? Because in natural system, actually, I think the supersaturation state will change a lot, related with the water chemistry. I don't know if you have a comment on that.
Well, I tried to add chemistry to this model, and I made a couple stabs at it, but I haven't been able to do it yet. I'd like to put in surface areas and surface energies and solubility products and so on, but I haven't done that yet.
Okay, so you assume a constant supersaturation state?
Yeah.
Oh, okay.
Yeah.
Thank you for the talk. I'm surprised not to see any merging of two crystals. Is it something that is not important at all?
No,
would it give?
That's important. The law of proportional effect shows us that it's not one atom at a time growth, but rather chunks of crystals grab onto other bigger crystals. And that's the way it grows. If it didn't happen that way, we wouldn't get a log normal distribution. Okay, thanks.